I'd like to welcome everyone to the third session in our IMRT curriculum. We're very excited to have you. We've had fantastic turnout at the first two lectures. Today we're very honored to have Dr. Teruel from NYU in New York City in the US giving us a presentation on physics safety and shielding implications for those of you designing vaults or wondering if you have a vault that is capable of making the upgrade to IMRT given the increased requirements that places on things. So we can make this interactive in that if you have a question, please type it into the text box and we can try to answer some of those questions as we go. And then certainly at the end, we will have a question and answer session as well. So without further ado, we thank you, Dr. Teruel, for presenting today, and I'll turn it over to you.
All right, thanks, John, for the presentation. It's my pleasure to be here today giving this lecture. So I'm going to be talking about safety, mostly regarding to shielding and radiation survey, and also limits and recommendations and regulations. So I'm going to start here. So what's the purpose of radiation shielding? Of course, is to minimize unnecessary radiation exposure to everyone in your department, including patients, members of the public, radiation workers, and any other employee. Besides the limits that we're going to talk about, I wanted just to throw this concept right away of ALARA, right? That it means that we want to maintain unnecessary exposure as low as reasonably achievable. So not even just try to just focus on a limit, but we want to reduce occupationally exposed individuals as low as possible. So we are going to attempt to reduce regulatory limits to 10% based on ALARA. So where do we get these recommendations and regulations in terms of exposure of occupationally exposed individuals? So here in the US, these are some of the bodies. I want to mention there's more, but main ones, ICRP, the International Commission on Radiological Protection, which primary function is to evaluate the information with respect to biological effects of radiation. And it provides radiation protection guidance. Then we have the NCRP, the National Council on Radiation Protection and Measurements. Primary function is to review ICRP formulated recommendations and develop ways to include them in the US radiation protection criteria. So these two organizations provide recommendations. And then we have the NRC and the agreement states that actually enforce those recommendations. They make it into regulation. For Linac, it's the states actually, the ones that enforce, use the NCRP recommendation and enforce those. So we're gonna talk a little bit about units. When we're talking about radiation protection, we're gonna use Sievert instead of Gray. And the concept is the same, a joule per kilogram, but it's gonna be affected by conversion factors. So we go from absorbed dose in Gray, we're gonna use radiation weighting factor. That's for photons, it's gonna be 1, but we know for neutrons, it's gonna be variable depending on energy. We're gonna write to equivalent dose. And then again, for Linac, this tissue weighting factor is gonna be 1 for the total body. But if you were gonna look at individual organs, you have tissue weighting factors to get to an effective dose. And two units that you're gonna see a lot as well, and you're probably familiar with is, they're non-international system units, but it's the rad for absorbed dose, that is 1 centigrade, and the rem for effective dose, that I think is more common to see. That is equivalent to 10 millisievert. Another unit that is important is the one you're gonna see when you use your survey meter is exposure. So exposure is defined as the amount of ionization created in air. The international system units is coulombs per kilogram, but also it's good to be familiar with the Röntgen. That is the special unit. Here you have the conversion. How this translates, because this is exposure in air, how this affect what will be deposited into tissue in someone that is in the other side of the barrier. You have this conversion factor of 0.96 centigrade in tissue per Röntgen. But for radiation protection purposes, we just take it as unity. So for radiation protection, we always go as conservative as possible. And you maybe heard the expression like 1 rad is a rem is a Röntgen. So basically we're gonna make it 1, the conversion factor. So let's talk about personnel. You're gonna have two types of exposed individuals. So you're gonna have radiation workers. These are the people that may receive more than 10% of the applicable annual limit of exposure. You can think about your therapists, physicists, everyone basically that has access to control areas and the people that wear a personal oximeter, right? But then in your department, you're gonna have more people. You're gonna have members of the public. You're gonna have patients. You're gonna have the visitors that come with the patients. You're gonna have other employees not directly related to treating the patients. So these members of the public, they're not allowed to freely access control areas and do not wear a radiation badge. I'm talking about occupational exposure. So everything we're gonna discuss today here, it's gonna be related to plant exposure, right? That's the exposure that arises from the plant operation of a source or from a plant activity that results in exposure due to a source, right? And this can be controlled by a good design of facilities, right? Like good design of your shielding, a proper equipment operation, right? And having training and operation procedures in place. Of course, there's other sources of occupational exposure that can be emergency exposure, right? And you can think, outside of maybe the topic of today, but for HDR, if you need to go into the room to hand crack an HDR unit or things that are not planned regarding to shielding, but that, a radiation worker could be exposed to. But for today, we're gonna focus in the plant exposure and how to control it. So we're gonna look at the total effective dose equivalent. You can also find this term referring to the same maximum permissible dose equivalent. And this is how the NCRP and the states regulate this, recommend and regulate this. So for radiation workers, the recommendation is less than 50 millisievert per year. And when we move to regulation, we're gonna determine by week. So it's gonna be 1 millisievert per week. For public, non-badge employees or anyone else in the department, that's gonna be 1 millisievert per year. And in terms of regulation, it's gonna be a term per week, it's gonna be 0.02 millisieverts per week. Note that I make here one note, and is to declare pregnant workers. So if a radiation worker pregnant that declared the pregnancy, that limit is decreased by 10%. So it cannot be more than 0.5 millisievert per month. And also, there's recommendations regarding individual organs, right? You can see in the NCRP limits for eyes, extremity, skin, and how we use a LARA to actually decrease those to 10%. So we talk about personnel, now talking about areas. There's gonna be two types of, basically for radiation shielding purposes, two types of areas. You're gonna have control areas. These are areas where radiation warning signature is required. And as I said before, they're only freely accessible by radiation workers. And then you're gonna have uncontrolled areas. These are any area in the department that is freely accessible to the general public and radiation warning signs are not required. So for shielding calculations, the NCRP recommends a more strict shielding design limit for control areas. So I said that these are the limits for radiation worker and the public. Actually, when you design your shielding, you're gonna follow a more strict limit for the control area. That is like a 10% decrease, right, from the regulatory limit. So you're gonna have two design goals, basically. 0.1 millisievert per week for control areas and 0.02 millisievert per week for uncontrolled areas. And of course, I'm talking mostly like a US regulation, but always follow your national guidelines and regulatory agencies, right? Or, you can refer to International Atomic Energy Agency. Here's table 2 of this safety report series number 47, and you can see a comparison between the International Atomic Energy Agency recommendation, USA, and the United Kingdom. So you can also compare it with your own guidelines. So what are 3 main factors affecting exposure to occupationally exposed individuals? So time, obviously, is the exposure to radiation increases linearly with time. If you spend double amount of time at the same distance, you're gonna be exposed to double amount of radiation. Distance, the exposure to radiation is inversely proportional to the square of the distance. So here you can see, like if you move from 1 meter away to 2 meters away, you're gonna decrease your exposure by a factor of 4. And finally, shielding. And the exposure to radiation is inversely proportional to the shielding material and thickness, right? And we normally will talk about half value layers, 10th value layers. So you can see here, like if you are behind this barrier or behind this barrier at the same distance, you will expose to half of the radiation. So I mentioned earlier the shielding design goal, right? So I just wanted to show you where this come from, like what's the formula, for instance, for the primary barrier transmission, because it's important to know, even if we're not going to do directly shielding calculations, we want to know which factors are involved in case you need to look back and see why a measurement might not be as good as you thought. So here P is your shielding design goal. And as I said, we basically have two numbers for control 0.1 for uncontrolled 0.02 millisievert per week. And the rest of the parameters, very important, is the workload, the use factor, and the occupancy factor that I'm gonna talk in the next slides. This just the distance in meters from the isocenter. It will normally be at 1 meter to 1 foot outside of the barrier where you're gonna measure during your survey. And this will calculate your barrier transmission. So when you are designing shielding, you know how much shielding you need to add. And as I said, the workload is a very, very important factor, right? The workload is basically the amount of dose per week at isocenter. So maximum amount of dose expected to be delivered to a reference point, normally the isocenter, in 1 week. And here you can see it's gray per week at that 1 meter distance. And this is very important because this is going to drive very heavily your calculation. And you have to be aware that, and I know this is very important for like clinics going to IMRT or doing more modulated treatments, the workload for leakage for a secondary barrier actually can be higher than the primary workload. Because as you go to use modulated treatments, you're going to use much more MUs for the same amount of dose delivered, right? So you need to recalculate your workload for leakage, and you basically have two factors to account. Is F here will be the ratio of modulated treatments, and CI is your modulation fraction. And you can think about the modulation fraction and the number of MUs per 1 centigrade delivered, right? For open treatments, you can just say 1 MU per centigrade, or, you know, otherwise you're gonna have like 1.1 something. But for modulated treatments, actually, you're gonna need many more MUs, right? To the factor of 2, 3, 4 times. Occupancy factor, right? This factor accounts for the people behind that barrier, right? So when you have an occupancy factor of 1, and this table is right out of NCRP 151. So when you have someone like something like an office, right? Or a control room for a Linac, you know that area is always occupied by the same individual, or the same individuals, right? So the occupancy factor is basically 1. Then you have other areas that you don't expect the same person to be there for the 40-hour week, like an adjacent treatment room or a patient exam room. So it might be the same people, like the therapist or the physician, going into a room, but they're not gonna be there for the full time. So these get reduced to 1/2. And then you can see the rest in the table. You know, the concept is the same. It's like, is the same occupant in the room? Is the room always occupied? So the factor will start to decrease and these are the factors that you can use for some example, like the treatment vault doors, like we reduce it to 1/8 because it's very rare that someone is right there at the door, right while all the treatments are being done. So someone could walk through the door, but it's reasonable to reduce the factor there. And you can see all the examples in NCRP 151. And finally, the use factors. So this is the proportion of the time that the gantry points in a particular direction. There's an updated table in NCRP 151 that it has the use factor at 45 and 90-degree intervals. And still for practical purposes, assuming 0.25 for each of the cardinal angles will work. And this, you can already think about, you're measuring your transmission through a primary barrier. You only care when the amount of time that the beam will be pointing to that barrier, right? So maybe when the gantry is at 90 or when it's at 180 or 0. So you are not gonna have your gantry all the time that is on pointing towards the same barrier. So I showed the formula to perform calculations, and we all have performed calculations as part of grad school or residency, but When it comes to like designing a new bolt, it's very important that you don't design the new bolt just based on your own calculations, right? So I wanted to stress that here. In reality, most of shielding calculations for new bolts are performed by a small number of radiation protection and shielding experts, right? So always get advice, get someone to look into your calculation, get someone else to do the calculations, you know, and here you have organizations you can reach out if you need help with this. Some calculations to estimate how changes will affect your shielding are okay. If you already have shielding and you're changing something or transitioning to, you're adding a new energy or transitioning to IMRT. But still, you know, this is a very important. So it's always advised to reach out to an expert. So what are the sources of radiation in a Linac bolt? So if you look at this graph that I made, if you just think that this is the gantry and you're looking at the plane of the room, so here you have a primary barrier, and you'll have you're looking to the floor. So one of the sources is the primary radiation, right? So this is basically your gantry will be at 90 degrees and just the radiation will be incident in this barrier. Then you have leakage radiation, right? That's just the radiation that from the Linac head, right? That doesn't get fully shielded by the Linac head. That's gonna go in any direction. You also have a scattered radiation. That's gonna be radiation that's scattering the patient. So maybe your beam still pointing to that barrier, but the radiation will scatter in the patient and then go to the secondary barrier. And also photoneutrons, right? For Linac energies higher than 6, normally considered 10x or 10 MV or higher, you're gonna create neutrons, mostly in the Linac head, and those are gonna go isotropically in every direction. So regarding radiation survey, when are you required to perform a radiation survey? Obviously, when you have a new facility, right? You have a completely new bolt and a Linac accelerator, you need to do a survey. Also, when you have an old installation that has been modified, maybe you're replacing an older Linac with a new model. You need to do a survey to make sure you're still under regulatory limits. Or even when you're adding new procedures, right? Maybe you're adding 15x to a Linac that didn't have 15x before. So now, the energy is gonna be more penetrated and you need to make sure that your shielding still apply. The same for introducing IMRT or rapid arc. You're gonna have more modulated treatment. That's mostly gonna affect your leakage. Introducing flattening filter beams for SRS, or even starting a total body radiation program where you're gonna have the beam on time increase significantly, depending on how many treatments you're planning to do. So regarding instrumentation, here you can see like the main instrument you're gonna need is your ion chamber surveymeter. That's the main tool for radiation surveys. You can measure in rate and integrated mode. So here, this will be like the rate measurement. And this one actually does the integrated at the same time. You'll see it at the bottom. The range is very high, like you shouldn't expect readings like this anytime in, under shielding. And there's several manufacturers and models, and there's digital analog devices. You're also gonna need a neutron detector if you have high energy Linac. So the threshold for photoneutron production depends on the material to which photons are incident. For the materials present in the Linac head, the lowest energy threshold for photoneutron production is 6.2 MeV for lead. And you have tungsten, copper, and that now have a higher threshold. So again, it's something like when you have a high energy Linac, you need to consider. They measure directly in millirem per hour. So easier just to, when you feel your pressure, you already have that number there. And during calibration, the response to the photons is evaluated just to make sure that, that it's not over-responding to photons and you get a measurement that is higher than expected. And this is actually a pretty heavy detector. It doesn't look like that. When I was doing a radiation survey with some of my fellow residents like a year and a half ago, we're like, okay, now is your time to get the neutron detector, because it's here you have this cadmium linen moderator, and then inside you have your detector. So it's actually heavier than it looks. And then another detector, the Geiger-Müller counter. So I just want to point out, you should not use this for radiation survey or quantify exposure. Still, it can be useful, and is mentioned in some of the reports, like to find cracks or a hole in the shielding. But again, be really careful when you use this, because you know this is going to have an avalanche effect. Like, you shouldn't really trust the numbers. You know, use your ion chamber survey meter for that. And regarding calibration, you need to ensure that all your survey meters are calibrated, right? Here we calibrate them every year. The detector model and calibration date needs to be included in the shielding report. And also your calibration report for the instrument should include date of calibration, the new due date, results at time of reception, results after calibration, and source used for calibration. So that's very good to make sure that there's nothing wrong with your detector. When you send it for calibration, you're gonna see, this is a screenshot from the neutron detector. They are gonna perform measurement before calibrating the detector. So you can see there's not that much different, like 0.45 to 0.5. So that's a good way to spot if something, your detector might have any issue. Suddenly you have a very strange number when you send it to calibration. And they're gonna include the source they use for calibration. And also, as I said, for neutron detectors, they're gonna make a comment of, they're gonna verify that it's not gonna respond to gamma radiation. Okay, so we're gonna get to more like to the fun part, like, okay, we're ready to do a radiation survey. So we're gonna need to do 3 measurements. For a new ball, a new equipment, the first one you're gonna do is a Linac head survey. And this is to ensure your leakage calculation is accurate. Then you're gonna do an initial survey prior to commissioning, probably right after acceptance, just to make sure. So in this one, you don't need to make your output right on, right? You just need to make sure that everything is good for you to be doing commissioning, right? You're gonna be using the beam for a long time during commissioning. You need to make sure your shielding is good. And again, when you're completely done with your commissioning and you have your output perfectly tuned, you're gonna do a final survey, and this is the one that is gonna go to your final report. So for the Linac head survey, and as I said, the important part here is, like, if you look at the formula for leakage calculation of shielding, you always have this 1000 factor here, right? So that factor comes from a regulatory limit that says that you cannot access 0.1% of the intensity at isocenter outside of the Linac head, right? So, any point like 1 meter from the target that is not in your isocenter, out of the Linac head, it should be shielded to at least this limit. So you need to verify that, because if not, this calculation wouldn't hold. So the way to do this is to basically wrap the Linac head with the portal localization film. And it's important to number. So maybe you can see here 13, here 5. So you need to dark number those films, add the orientation of the films. Then you're gonna deliver enough MUs to darken the film, but without saturating it. I think we did around 300 MUs. And here I put like which film we use and like the limits. And then you're gonna look at the spots that get darker, and you're gonna measure with a densitometer only like in those highest darkening spots. And then finally, you can confirm with the ion chamber. In our case, we use a profiler, an ion chamber profiler. So we have more like an area, you just verify where you have your maximum dose and, around the area that the numbers make sense, that you are within that limit. Okay, so now we're gonna go to the proper Linac shielding survey, right? So first thing, of course, plan your survey. Get your blueprint, look where your Linac is, look what is around, and mark where you're gonna measure, and mark what is this, a primary barrier, a secondary barrier. This is the control room, so secondary barrier with occupancy of 1. And also we didn't have anything below that floor, but you need to account for anything. In this case, we have a floor on top, so we also need to check the primary barrier there, the secondary barrier there. So let's get your blueprint and make sure you mark every place you'll need to check. Oh, and just to point out here, like sometimes like, you have maybe the physics part here. So you want to take a second measurement. Even if you're checking the full barrier, is good to, make sure you have everything accounted for around your electrical panel. When in doubt, like always, doing an extra measurement doesn't hurt. And regarding energy and dose rates, so you're always gonna do it like worst case scenario. So you're gonna perform the survey for the highest energy and the maximum dose rate. So for instance, we use 15 MB with 600 MU per minute. And how you're gonna set up for the survey, right? So for primary barriers, and again, this goes back to we're gonna do it worst case scenario. So you're gonna orient the gantry to that barrier. So here we're gonna measure in this barrier, the area that we use the number 3. We're gonna open the jaws to the maximum field size, and we're gonna rotate the collimator to 45 degrees. So basically we're gonna try to cover as much as the machine could do, even if that's not really realistic, that's gonna be happening. But you need to make sure that in the worst case scenario is working. So, and of course for the primary barrier, you're not gonna place any phantom in the path of the beam. And again, this is also like worst case scenario, right? When you're treating, you're gonna have a patient there, there's gonna be attenuation. But for our survey measurements, we're just gonna leave it empty. So it's exactly like the worst situation. For measuring behind a barrier, you're gonna measure at about 1 foot. This makes sense in the sense like you're worried about the people behind that barrier, and it's pretty unlikely that people are just laying against the wall, right? So this 1 foot is normally used like 30 cm from the wall, and also from the floor to at least 6 or 7 feet. So this is already, it will cover like if someone very tall is there. Again, like you don't need to go with a ruler for these measurements. I would say, just make sure that you're not measuring right against the wall. That's not necessary. And it's important to measure the edge of the primary barrier. So this setup doesn't work for secondary barriers. So you cannot measure both, just measure primary and then come here and measure secondary, because you need to change the setup. But you should actually go to the edge and make sure you have a sharp decrease. You need to make sure that you are really covering with your primary barrier what you should be covering. And of course, you have to be thorough, but also minimize your exposure and wear your badge. Like, there's no need to be there for a long time. Just make sure you measure all around and, numbers make sense. There's not like a spike at any point. So now we're gonna look at the setup for the secondary barrier. So here you are now, so imagine we're in the control room, right? You're evaluating the shielding for scattering and leakage. Like the beam, this gantry is never gonna be pointing again this wall. So you're gonna maximize scatter conditions. So you're gonna open your jaws, you're gonna place a phantom in the beam, you can just use your water phantom. Leakage is not that much affected by setup, so you can just leave for that for the leakage as well. And you're gonna measure at 4 different cardinal angles. So you're gonna make sure that the numbers are consistent, or just take the worst number, or when also you have to fill one row of the survey. You could even use your use factor to average that, but you can just measure the 4 different cardinal angles and take the worst value. And it's always important to pay closer attention to your physics board, HVAC, electrical panel, anywhere that you think that it won't be good to have a higher reading, or that there might be a slight higher reading because of the conduits, just make sure you're still good there. And the most likely scenario is that leakage radiation is the main factor for secondary barrier shielding, maybe with the exception of the primary-secondary barrier interface, so the smaller angle of scatter. So regarding neutron shielding, so as I said before, neutrons are produced by the interaction of high energy photons with the Linac head materials. Photoneutrons are emitted isotropically, and concrete is a great shielding material for neutrons, has high hydrogen content, but lead or any other high C materials are not effective as shielding for neutrons. And of course, you have to be aware like neutron capture produce gamma emission. Still, if your barrier is concrete, should not have any problem because it's a great shielding for the neutrons and for the photons that are produced. But the main locations to survey for neutrons are at the end of the maze, again, at any conduits that might, produce like the particle to go without attenuation, without interaction, and directly shielded doors. So here in New York, we have a lot of these directly shielded doors. And it's very important to measure there for neutrons because that's, it's not going to be concrete, right? It's going to be like a mix of high C material and like polyethylene. And so it's important to measure there. So now moving to control and uncontrolled areas. So both control and uncontrolled areas could be adjacent to a Linac bolt. And you can consider surveying an uncontrolled area that is located very close to a Linac bolt, right? For instance, here we took an additional measurement. This is a corridor and it's just behind the control room. So you can also estimate based on the distance, but again, never hurt when you're doing your radiation survey to be extra cautious. And a couple of concepts, you can see this in all the reports, just to consider as like ground shine, right? Like what if your shielding depth actually doesn't prevent to have like this kind of like interaction, and then you have like some high reading around here. So always like be thorough doing your survey, and the same for sky shine. In the case that, there's nothing on top of that bolt and, this is just a street, if this shielding wasn't done properly, you might have some radiation now scattering back. So, when you do your survey in this area, make sure to account for this. Some safety tips for performing surveys. Of course, equipment functionality. Make sure your equipment is working properly, is calibrated. Redundancy, if you have more than one survey meter, just bring it, and it might be more than 2 people involved in the survey, so someone can carry the other survey meter. Maybe the radiation safety officer has its own dedicated equipment as well. So any redundancy is great. Also have an idea of what to expect. Observe your shielding report prior to the survey. Which readings are you expecting to get? Do you have a similar bolt that was designed, with the same goals and in the same way, with the same equipment? So you probably should get similar results, right, for this other bolt. And again, be thorough. You're not going to perform radiation surveys periodically. So, let's make sure you get everything that you need. And of course also, but be safe, right? You don't need to spend 15 minutes behind a barrier, right? And something very important too is the communication between the Linac operator and the surveyor or surveyors. Make sure you have direct communication with the person that is operating the Linac. It's always better be safe than sorry. You don't want to walk upstairs to a primary barrier and then suddenly find out a very, very high reading and you cannot tell the person to just beam off. Well, might take you longer just to exit that primary barrier. So for the same reason, turn on your Linac prior to entering the area you're surveying, and also have your radiation detectors on so you can spot any issue as you approach the barrier. And also very important, just pause signage when you're doing your survey. Make sure no one will be accessing the areas to survey. It can happen that maybe a new facility, there's still some construction going on, and there might be people, or constructor around. But, you want to make sure that, again, you don't walk to the ceiling and there's someone, standing right there where you have now your Linac pointing and beaming on. So, outside of the barrier, but still, make sure that the area that you're going to survey is clear and that anyone that might be in the building is aware that, which areas should not be accessed. Okay, so talking about results, we're going to look at 3 quantities. The first one is the instantaneous dose rate. So this is the measurement that you obtain in rate mode using your survey meter, right? We don't have it in the US regulatory limits regarding this. The exposure would be 14.7 milliradian, right? And, always be cautious when looking at this number because maybe, at least at my first time doing a survey, sometimes you can think, whoa, this looks high, and in your mind, you might be like, oh, well, 4-hour week, a 14.7 milliradian per hour, don't panic. That will represent a very high number, but in reality, think about your actual beam on time treating patient that is built into your workload, right? Think about the use factor, right? Your Linac is not gonna be 40 hours pointing to that barrier on, right? So it's important when you look at this number just to have that in context. So the second quantity is the time average dose rate in 1 week, RW. So this quantity you can calculate multiplying that instantaneous dose rate by the time by T, that is your average beam on time per week. And here is the one that you need to ensure. This is the measurement that you need to focus to ensure your goal, right? So this measurement has to be lower than your design goal divided by the occupancy factor. Or you could just move this T here, like multiply your occupancy factor by your RW, and that has to be lower than your design goal. And remember, your design goals are set 0.02 millisievert per week for uncontrolled area, 0.1 millisievert per week for control. The third number you're gonna look at is the time average dose rate in any 1 hour. So let's say, you did your calculations, assuming a number of patients per week, with this average of number of patients per hour. So what you're gonna do to get this number, you're gonna divide that RW that was per week by 40, assuming 40 working hours per week. And then you're gonna multiply by this factor. M is the ratio of the maximum number of patients that could be treated in 1 hour to the average number of patients per hour, right? So just think about I design my calculations for an average of 4 patients an hour, but maybe this, if we need to do 5 patients in an hour, we'll do it. So that'll be the max that we'll do. So you need to do 5 divided by 4. That'll be the factor that you're multiplying here, right? And the goal for this, it has to be less than 0.02 millisievert for any given hour for uncontrolled areas. Okay, so let's move to what is in your report. So at the end of your survey, you're gonna have a report and you're gonna have the days of the initial and final surveys, participants, an overview, Linac model, serial number, equipment that you use with the calibration date of each of your radiation meters, the radiation survey parameter. You're gonna have your workload, a blueprint with the areas that you survey, and you're gonna have your detailed measurements, and also a statement of results according to regulation. So, as a conclusion, this measurement, we can justify we're meeting all the regulatory limits. So let's do one together kind of thing. It's already filled out, but I'm gonna go step by step. And as I said, we're gonna provide with a spreadsheet, so you can have a handy way to perform your survey if you need it. So remember that picture that we have a primary barrier in zone number 3. So, okay, we're gonna fill out zone number 3. What is that location? Is Linac bolt? What type of area? Control area? What type of barrier? It could be primary or secondary. So first a primary one. What is the use factor? So it's a primary barrier where it's gonna only be hit when the gantry is around the 90, right? So it's gonna be 0.25. What is the occupancy factor? So we said that for an adjacent Linac bolt, we were gonna use 0.5 based on NCRP 151. What is your workload? So here, this is just an example. I put 500. I think NCRP 151 recommends 450 is gonna be the most common one, but we're gonna use 500 for this. Where was my gantry? Obviously, it was at 90, so I can have that primary barrier, the beam incident to that primary barrier. Field size, as I said, maximum opening with the collimator at 45, so I can maximize, in the corners, the primary beam. Do I have a phantom in the beam? No. Energy, highest, dose rate, highest, right? So you'll be filling all this in preparation, and then you can go do your survey, and then you're gonna fill this second part. And you're gonna be, okay, what did I get? What was my photon measurement, my instantaneous dose rate? So I got a reading of 29.6 in the worst area. What did I get for neutron? Because I had a high energy. So I got a pretty low 0.1 millirem per hour. What is the time, right? Because we need to multiply this factor by the time. So here I put how I calculate the time here, right? You're gonna have your workload, so that you have it up here, you have 500 sievert per week. You're gonna multiply by the use factor. So actually how much of those, sievert are gonna be delivered in that direction. And then you're gonna divide by the dose rate. And this is just 600 MU per minute, where I just made an equivalence of 1 MU, 1 centigrade, and I moved to hour instead of minute. So we get average time on of 0.35. So I plug it there. And for the neutrons, I'm just gonna say the use factor, I'm gonna use 1 because they're gonna come to the barrier from any orientation of the gantry, so 1.4. And now I'm gonna calculate my RW, right? So you're just gonna multiply this by this, and this by this. You put it together, basically, it's gonna be the photon measurement dominating this, you get 10.5. We don't stop there because if you remember, our goal is gonna be that this is lower than your design goal divided by T. So I'm gonna multiply this number by T. There's the occupancy factor, 0.5. You're gonna get 5.25. And I underline these 3 because, this is the important part here, right? This is what I need to compare. This is the regulatory limit, and this is the recommended limit. So perfect, right? So even if, you thought this might be a high number, you can see your primary barrier shielding goal is actually very well covered. And again, we're doing the survey with the very worst case scenario with nothing in the beam fully open, pointing to the wall. And finally, even the regulatory limit in any 1 hour doesn't apply. As I have it in the column, I'm gonna do it. So I'm gonna assume, in the worst day, I can treat 1.5 times the patients that the average in 1 hour. I'm gonna multiply this by RW and divide by 40 hours a week. I get 0.2 milligram per week. Oh, sorry, it should be per hour, any given hour. Again, let's do a second one, now with a secondary barrier, right? So we're gonna make it a bit more, not complicated, but we're gonna cover the leakage workload. So now we're looking at Zone 2. This was a control area. This area is a control. This barrier now is a secondary barrier. The use factor is gonna be 1 because it doesn't matter where the gantry, the orientation of the gantry for the shielding of this barrier, right? The occupancy factor is gonna be 1 because that's what applies for a control area where you have the therapists that are the same people all day working there. Then the workload for the primary barrier was 500, but my workload for leakage, if you remember the formula, I came out with a number that is actually higher. And just want to point out here, I put in MU per week to make it make sense for the calculation, because it's not that suddenly I'm going to use more, radiation. It's actually to deliver the same amount of gray, I'm going to need to use more MUs, right? And I should add here, these factors multiplied by 100, right? Because it's actually MU centigrade. So this number is actually multiplied by 100. Then we're going to have the gantry at 0 for this measurement, but we are going to, this will be repeated for any cardinal angle. We're going to have the field size 40 by 40. We're going to have a phantom in the beam. And again, we're going to use very, worst conditions, a higher energy, higher dose rate. So I get here and I get this measurement of 0.7. My neutron measurement is negligible. And then I need to calculate my time on. And this might looks a bit counterintuitive, but because the reality is like your beam on time, mostly with modulated treatments where the dose rate is adjusting, is gonna be variable during the week. So at the end of the day, when you're looking at primary barriers, you just make the case of what will be the beam on time of, maximum dose rate to deliver all the dose, right? And that would be equivalent. That's exactly what we did in this previous slide. For the leakage calculation, we're gonna use the leakage workload, and then it's gonna look like the beam on time is higher, and actually that makes sense in the sense that the time to deliver that amount of MUs at a dose rate is this time. But actually the beam on time could be none of those numbers when you're treating patients, right? Because those modulated treatments might not use your highest dose rate. Actually, they're not going to be using your highest dose rate all the time. But still, for our shielding calculations and comparison, is equivalent. And again, just think about these two numbers are both multiplied by 100 because it's actually mu will be the equivalent to centigrade. But that cancels, so this result still holds 4.17. So now you're going to multiply these two numbers. You're going to get your RW, and you're going to multiply by your occupancy factor. So you get to 2.92. And again, you compare, this is my regulatory limit, this is my recommended limit. So all good. I'm actually well below this limit, right? And again, I'm going to get the any given hour number. So I'm going to multiply 1.5 and divide it by 40, and that's 0.11. Because this is a control area, this limit doesn't apply. This will only apply for an uncontrolled area. And we know it's 2 milligram in any 1 hour. So can we make this secondary barrier uncontrolled looking at this measurement? Because I will be meeting this any 1 hour limit. But the truth is, if you look at the regulatory one, that will also drop to 2. So no, this has to remain a control area. If this was an uncontrolled area, we wouldn't be meeting that limit because we'll be over, right? We get 2.92 instead of the 2. But for a control area, we're doing very well. Okay, so I have a couple slides about moving from 3D to IMRT, as I think that's a very important topic for the audience. So one thing that might seem counterintuitive is that your radiation survey readings will be the same, right? I mean, if you are pointing your gantry fully open to the wall, just because you're going to start doing IMRT, that doesn't change anything. You're going to read the same with your detector. So what is changing? Well, your workload is changing, and maybe your use factor is changing, right? And those were built into calculating your shielding needs. So regarding primary workload, what could happen to increase your workload? You're moving to IMRT. Well, maybe you will be treating more patients. Maybe you will use some dose escalation with the new functionality. So the average dose you treat the patient might go high. And remember, your workload are gray or silver per week. If your workload increases, your transmission factor decreases. And that could result in the need of more shielding if now you're not meeting your design goal. But the main influence is going to be secondary barriers, as I said, mostly because of leakage. For conventional treatments, we assume 1 centigrade, 1 mu. For IMRT treatments, you're going to need about 2.5, even maybe to like 5 MUs for very highly modulated treatments. So, think about moving from a 3D to IMRT with the following. So you have an initial workload, but now you're going to do half of your treatment using IMRT, and you're going very conservative. You're using a high modulation factor of 5. If you just plug that equation that I showed before, excuse me?
I think it was just a stray microphone. You can continue, okay. Jose. Thanks.
Right. So the take-home point here is like you're going to increase your workload. I choose a kind of like high number here, but the take-home point is like you're going to increase your leakage workload by 3. So how do you account for that? I mean, again, your survey results are going to be the same. Well, think how that number is affecting your calculations, right? So this was your goal that you need to meet. This is how you calculate your leakage transmission factor. So what's happening is now you have this leakage workload that is 3 times your 3D, right? And because this, you don't want to change this and you haven't had any shielding yet, so you haven't compensated for that. One way to look at it will be, well, now I need a revised criteria. This criteria doesn't apply anymore. I need to meet this now. I need to meet my RW has to be, multiplied by 3, has to be lower than this to still be within my limits. Or you can think about, well, how much shielding, if I really want to be at the same point that I was, how much shielding would I need? So you could just look, so this is the formula for the number of 10th value layers for any barrier. If you already have that calculated for 3D and now you're going 3 times higher with IMRT, if you just plug that in here, you're gonna have your additional 10th value layers from what you already have is gonna be 0.48. But of course, I mean, if you're meeting this, you might be fine. It's just, you're gonna have more exposure at the end of the barrier, but still very well within regulatory limits if you're still meeting this criteria. Okay, so I think, all right, so we're around time. Just hopefully you don't mind staying 5 minutes or 3 minutes with me, just to talk. This is the last topic, talking about remediation. So what are possible sources of error? So maybe something changed after shielding calculations, right? Your ISO center got moved or something happened there. Shielding material density or thickness, issues during construction, calculation error. And again, just to reiterate, always look for advice when doing calculations for a new bolt, right? Get an expert to do it or get involved with you in doing it. So I got a different number than expected. Now what do I do? Well, hopefully nothing. I mean, for example, if your limit for a primary barrier, you expected that you were gonna get 0.05 millisievert per week, turns out to be 0.08. Well, obviously there is a deviation, but you're still under recommended and regulatory limits, even with a lot of considerations. So, it's fine. You're actually meeting everything you wanted to meet. Might be a small deviation, but that's it. Different scenario, you get a reading that is much higher than expected or that does not comply with regulations. So I'm gonna show you 3 ways to dealing with this. Very obvious, additional shielding. This is gonna be the only solution to achieve a shielding goal. It's gonna be a burden in terms of money, time, space. You might need to move to using high density material. You need to design a plan that minimizes how much space you need, probably inside the bolt. So, it's one approach, but it's not the only one. You could recharacterize an area. If your goal limit was not met for a control area, but it is acceptable for a control area, well, maybe just recharacterize that area. It will restrict access to other people, and it requires signage and affect maybe how you were planning to use the space. But while not optimal, it'll probably be more cost effective. And also look back to, the formula, how you calculate shielding. What factors are there that are driving your shielding needs? Can they change? Can you adjust them for the new, to meet your goals when you found this discrepancy? So you can look at your workload, the use of IMRT, the occupancy. You might think of reducing the workload. You might think of just reducing the IMRT workload from like 50% of treatments to 30% of treatments. You could think of staff limits. Maybe you're meeting regulatory limits, but you're worried that you won't meet the recommended limits if you have a declared pregnant worker. So maybe you need to, if it's a therapist, maybe reduce the shifts or other tasks that don't involve being in a control area. An office space may become an exam room, right? So you're decreasing the occupancy factor by half. So in essence, reduce any factor that will achieve a transmission factor that yields your design goal consistent with your measurement and within regulation, right? Okay, so here, some reference that you can look. Mostly what I use today for this presentation is NCRP 151, but you can look at all of this one. Also the report I presented at the very beginning. It's referenced here. Thank you very much. And I put my email here in case you have any questions, down the road, or you want some additional information, anything, please don't hesitate to reach out.
Well, thank you, Dr. Teruel. That was a really great overview, and I think as comprehensive, certainly, as we could expect to get in an hour. That was really, really informative. I was wondering if you have time and if you would be comfortable doing so, do you think it would be worth very briefly going over the PowerPoint? Sorry, not the PowerPoint, the Excel document that shows the calculations. Is that something we could just show them how it works so that when they open it up on their own, they'll be a little bit more oriented?
So I still have the fully modified, with the form template that I was given. So, but it will be, it'll look very similar to something like this. where they're going to have all these entries for all the areas that they define. So hopefully this was, and I could add to the document, I just don't have it like fully ready, but I could add to it like, some example, like here, like example results. So that will help.
Okay, excellent. I think that would be great. We'll get that posted in the next couple of days, and I think should be a useful thing. We'll also post the report, TG 151, that you were referring to, that has some additional background information. So thank you very much. Are there any questions that we could take now? I don't see any. Oh, sorry, go ahead.
I have a question. Were you involved in transitioning from 3D to IMRT back in the day?
No, I've been involved in the radiation survey, but not so directly. It was already IMRT.
Okay. Oh, I see there's a question, John.
Oh, here we go. So the question was, can you use the peak mode for area surveys?
So, if you're referring to the instantaneous mode, yeah, I'm not sure exactly what you mean by peak mode. But basically with the ionization chamber survey meters that I've used, you have the instantaneous or the rate. So as long as either you measure for a small period of time or what your cumulative measurement time was, you could use that. If you want to use your instantaneous reading, you can use that directly.
All right, great. Any other questions? Don't see any. We're gonna have our program manager, Noah, will be sending the points of contact at all of your clinics an email today that has the link to the Google Drive shared folder where we'll be putting these PowerPoint presentations and also the additional reports and the Excel documents. And he'll also include a link again to the YouTube channel that shows all of these presentations. Again, the presentation gets uploaded generally 2 to 3 days after it's delivered. Looks like we do have another question asking if workload for VMAT is similar for, I presume that means IMRT.
Yeah, so it's when you're gonna recalculate your leakage workload, right? You just need to account for how modulated your treatments are gonna be, right? How many MUs you're gonna be delivering per centigrade now with your technique. So definitely, everything I say applied for, just IMRT and also like rapid arc VMAT, as long as you consider, the right modulation factor, like how modulated your treatments are going to be. And you need to use for VMAT, like if you think, prostate treatment is like 3 times, maybe a head and neck is a bit higher when using VMAT. So, always think about the average, but be extra conservative. When in doubt, use a little higher number so you're the modulation that you're expecting for this new treatment situation. Even you might need to use, if you put something for a Sabernight, something like modulate a lot, you need to use even a higher modulation factor. So this applies to any modulated treatment, as long as you use a modulation factor that makes sense for the type of technique that you're gonna use and the expected modulation that you expect with that technique.
Great. I think we had another question. Someone was asking if there's any alternatives to wrapping the head of the gantry in film in order to detect leakage areas. I know that's also how we do it here, but are there any alternatives to that?
That's a great question, because actually we were wondering the same when we were doing that work, right, or wrapping the Linac. So, and we were thinking about, using that same profiler, maybe move the gantry around. So, but we didn't come to a final solution just yet. So, all right, so still what we did, and that we are aware that people are doing is to use the film kind of right now the only way to really make sure all the areas around the Linac head are covered, right, that you're not missing where the hot spot might be.
Okay, there was someone asking again about your opinions on overshielding. Not sure exactly what that applies to, but what factor of safety over your calculation maybe that you should be planning for?
Well, the calculations always, we're considering here worst case scenario, right? And you were using the guidance of NCRP recommendations. of course, there's also like, you don't want to just, put a ridiculous amount of shielding, because that's going to have a cost in materials, a cost in space. So if you follow these recommendations, in CRP 151, and you have an expert involved on doing your shielding, you should arrive to an amount of shielding that is conservative. It's going to make sure, everyone treated and everyone in your department is okay. But, you shouldn't go farther than that, I would say. Like, you don't want to really, when you are very well within recommended limits and, your calculation were done by an expert, there's no need to add extra. If that was maybe the question, you don't need to start adding extra, because that's not really going to, affect anymore. That, you're very well within recommended limits might actually be, just a burden in terms of like, construction, more expenses and space and all that.
All right, excellent. And again, I'm posting the link to the PowerPoint folder that will have all of them. Let's see, we have another question. Unlike 3D conventional radiation, are the factors that possibly result in 1 centigrade equal 2.5 to... Not sure I followed. Are you able to see the question?
Yeah, I think I can see the side. Yeah, so I mean, if I got it correctly, so basically it's your modulation, right? Think about, I don't know, like whole brain treatment, where you're treating 300 per fraction and you have maybe 320 MUs or 330 MUs, right? Total, right? So that's a factor of like almost 1 to 1 or 1.1 to 1. When you go to use IMRT or BMAT, for delivering maybe 180 centigrade for a fraction to the prostate, your plan actually will be having maybe 500 MUs. So that's where those factors come from. So you're dividing that 500 by 180, you're gonna get like close to 3 or 2 point something. So, for a head and neck treatment that maybe is more modulated, you'll get even a higher number. So those are just the recommended numbers of what we've seen from experience, like how many MUs your treatment plan needs to treat that amount of centigrade. So it basically, divide the total MUs that you see in the plan by the centigrade. And again, you can always rely in the recommendations, always go a bit more conservatively if you're in doubt. But, that 2.5 to 5 mostly apply for like IMRT rapid arc treatments.
All right, I don't think we have any other questions. Certainly, I appreciate you posting your email address at the end of the presentation, and people can get in contact with you if they have further specific questions, and we'll be providing some additional contacts both at Rayos Contra Cancer and also at the IEA for people that can help you with double checking these types of calculations after you perform them. As I think we've established, it's certainly important to make sure you have experts involved, people with experience when you're designing this for a vault that you're building. So again, I'd like to thank everyone for attending the presentation. We're going to have, so again, thanks everyone for attending. Thank you so much, Dr. Teruel, for a fantastic presentation.
Thank you. It was my pleasure.
Thank you so much.